Thank you all for coming to keynote speech. And before we start, I would like to remind everybody that if you have questions, you can type in the Q&A box. And later on, when the keynote speaker finish the speech, then I will ask the question from the Q&A boxes. If you rather to ask the question in person, then you can raise your hand and we can unmute your microphone and you can ask the question. We have 30 minutes for the keynote speech. So please, we need to follow the timeline. So the best way is typing your question in the Q&A boxes. Okay, it's 2 o'clock Pacific time and 4 o'clock Central time. Welcome everybody. Welcome back to the Wireless Power Week. This is keynote speech section number 2. And follow this will be our technical section 2. When all the authors will be presenting their paper in short and answer questions. Today, we are very honored to have Professor Bernard Carlson to be our keynote speaker. He is Vaughn Professor of Humanities and Chair of Department of Engineering and Society at University of Virginia. He is also a lecturer in the Tech Innovate program at the National University of Ireland, Galway. Dr. Carlson has a very long list of accomplishments. In the case of the time constraints, I will only mention that he has written many books about innovation and on the role of technology in civilizations. Innovation as social process, and the technology in world history. Particularly, I would like to mention his most recent book, Tesla, Innovator of the Electrical Age, has been translated into 9 languages. Dr. Carlson is an expert of Tesla's accomplishments. And I heard his talk before, and that's why we invited Dr. Carlson to give us insight about Nikola Tesla, especially about his work on wireless power transmission and his history. And we can learn a lot from history, especially the insight of Dr. Carlson. So now let's welcome Dr. Carlson. And Dr. Carlson, please share your screen.
Thank you very much, JC, for that kind introduction, and thank you to all of the organizers of, I'm sorry about that, the World Powerless Conference, World Wireless Power Conference. Got that wrong. My apologies. It's a great pleasure to be here and to talk to you today about Nikola Tesla and his work in this area. And I think in many ways, Tesla's work on wireless power was his most important contribution. For decades, we celebrated Tesla for the invention of the alternating current motor And indeed, that was an important contribution. Just as Edison's electric light, his incandescent lamp, set the stage for electric lighting, so Tesla's motor was essential for us to have the power systems, the electric power systems that we have today. So it was a critical component, the AC motor that Tesla worked on for the world that we lived in for much of the 19th and 20th centuries. But as we look to the 21st century and we look to all of the things that are being discussed at this conference this week, the applications for wireless power are so exciting and so important that it seems to me that we should be thinking about celebrating Tesla not just as the inventor of the AC motor, but as a visionary who first proposed wireless power. He's the individual who basically put this idea out there for engineers and for the public to start thinking about. So what I want to do with you folks for the next few minutes is talk to you about Tesla's ideas for wireless power. Some were spot on, some of them were not necessarily practical, but let's talk about what he thought was possible and what he tried to do between 1890 and 1905. Those were the key periods that Tesla was working on wireless power. Let me provide a little bit of background about Tesla and his early life. He was born in 1856 in the Balkans in southeastern Europe. His family was Serbian, but he lived in a small village in what is today Croatia. Almost all of his family, his father and his uncles, were priests in the Serbian Orthodox Church. But rather than follow the family tradition and become a priest, Tesla instead chose to study engineering at an early engineering school in Graz, Austria, the Johannem Polytechnic School, which is today the Technical University of Graz. There, Tesla saw a demonstration in one of his physics classes of a DC motor that sparked badly. And even as a young man, Tesla had a great deal of intellectual courage, what some people in New York City would call chutzpah. And he said, I'm going to invent a better motor. Now, to do that, Tesla wandered around for a number of years, studied briefly at the University of Prague, got a job in Budapest. And in 1881, while he was in Budapest, he was taking a walk in the park. He was reciting poetry with his friends. And there he imagined the possibility of a sparkless motor that was based on an ideal. Tesla always wanted to find the perfect way to develop an invention. He was like Alexander Graham Bell, a theoretical inventor. In other words, he thought up the idea first. He worked it out in his mind. He got that ideal clearly worked out, and then he would go build the motor. So the ideal that came to him in that park in Budapest was to make a motor with a rotating magnetic field. In other words, change the magnetic field in the motor's stator and not in its rotor. All the other motors up to that point changed the magnetic field in the rotor. Now, to develop this invention, Tesla had to learn a lot more about electrical engineering. And there were no electrical engineering schools or programs at that point. So Tesla did the next best thing. He went to work for the Edison organization. So he worked for a variety of Edison companies, first in Budapest, then in Paris, and then ultimately in New York City. And while he was there, he learned a great deal about how to troubleshoot and solve problems on the existing Edison electric lighting systems. But nobody was interested in the Edison organization in Tesla's motor, and above all, in any ideas relating to alternating current. So Tesla left the Edison organization, and in 1886, he got support from a couple of very smart businessmen in New York City, Charles Peck and Alfred Brown, who helped him set up a laboratory and bankrolled his patenting efforts. And with their help, he developed a new motor, the first practical alternating current motor that used two or more out-of-phase alternating currents. Peck and Brown helped Tesla sell those patents to George Westinghouse, and Tesla spent a year in Pittsburgh working on AC motor designs. But he found the routine engineering boring, and Tesla soon left. So where do you go when you're ready to do something new? You know, in Tesla's case, he went back to Europe, and he went in particular to the Paris World's Fair. This is the World's Fair of 1889, which indeed was when the Eiffel Tower was erected. But more than just seeing the Eiffel Tower, Tesla spent time in the cafes talking to graduate students who were working with a number of physicists in and around Europe, and in particular fell in with the graduate students that were going to go work with Heinrich Hertz. Hertz was a professor in Germany, and Hertz was the first person to figure out how to detect electromagnetic waves, the waves that James Clerk Maxwell had predicted some years earlier. Tesla was excited about this. He studied Hertz's apparatus, or he read up on Hertz's apparatus, and he returned to New York City, and he promptly repeated all of Hertz's experiments and studied them some more. Now, while lots of people were at that time interested in taking Hertz's work and Maxwell's work and coming up with a series of equations to understand the propagation of electromagnetic waves, what all of you folks know well as Maxwell's equations, Tesla had no interest in that. As an inventor, Tesla didn't want to develop the science, he wanted to develop an apparatus. So he souped up, he scaled up Hertz's circuitry, so he had a device that produced lots of electromagnetic waves. And this was his Tesla coil. And I've got on the slide here the basic circuit that is behind the Tesla coil. An interesting side note is some years later, Tesla went back to Europe for a second time, made a point to visit Hertz in his laboratory because Tesla wanted to tell Hertz that Hertz had it wrong, that while there were electromagnetic waves, and Hertz had demonstrated that they were transverse, Tesla always believed that the waves were longitudinal. In other words, they were like sound waves. There's no record in Hertz's diary of Tesla ever visiting, but we can understand why Hertz would probably not make mention of a visit from a crazy Serbo-American who was telling him he was all wrong. Now, you have a Tesla coil, you have a new device, which we today call a Tesla coil, but you're Tesla. What can you do with these electromagnetic waves? What's an application? Tesla discovered that if he held a Geissler tube close to his Tesla coil, it glowed on its own without any wire connection to this. And this suggested to Tesla the possibility of creating a wireless lighting system. In other words, you could get rid of all of the cords and plugs and extra apparatus that you had, say, in your home to basically illuminate Edison electric lights. And to get people excited about this, Tesla did a series of brilliant demonstrations, including the one that's illustrated here, which he did before the predecessor of the IEEE, the American Institute of Electrical Engineers. And what's going to happen in that woodcut shows is Tesla standing up there on stage, and he's holding two big, almost 3 or 4 foot long tubes that have got a small amount of gas in them. They're about to turn out the lights. Tesla, when the lights go out, will step between those two big metal plates, and the tubes that he's holding will light up instantaneously. And people were just amazed by this. And Tesla went on in these demonstrations to sort of tell people that I have the vision of a wireless lighting system for homes, and all you'll need to do is install metal sheets or even metallic wallpaper, and you can have lights anywhere you want in your room, and you just would turn the lamp so that it aligned with the electrical field. So Tesla, in the mid-1890s, patented all of the equipment that you would need to power lights and motors wirelessly. And he dreamed of pulling an end run around all of the other companies in the electrical field at that time. The telegraph company, the telephone companies, the power companies, because he thought that wireless power could replace all of the overhead lines that were being used by those companies. So he saw himself as really the 4G, the next generation of electric light and power. So he promoted his ideas in his usual fashion through lectures, through private demonstrations. You can see on this slide a private demonstration that he gave for the famous author Mark Twain, who was fascinated by Tesla's ideas, and lots of newspaper interviews. And then he stepped back and he figured that just like Westinghouse had shown up and bought the patents for his AC motor, somebody else would show up and buy the rights to his new inventions. But in the mid-1890s, people weren't ready for this next generation of power technology, and no investors, no businessmen came forward. This frustrated Tesla, but it led him to reconceptualize how he thought his system would actually work. Tesla always thought like a maverick. As I said at one point in my book on Tesla, if everybody is ringing the front door to a house, Tesla wouldn't go up to the front door. He'd go around and he'd find the back door to the house and he'd go in that way. He always thought like a maverick. Now, early transmitters like the Tesla coil that were producing electromagnetic waves produced electromagnetic waves, but they also produced an oscillating ground current or electric current that went into the ground. The question was, which one did you want to optimize? Which one did you want to maximize? The current waves being produced, the electric current waves, the radio waves being produced, or the ground current? Most early radio experimenters like Oliver Lodge or Marconi did what was shown in the upper half of this slide. They concentrated on sending electromagnetic waves through the atmosphere. So you go from the transmitter on the left, the radio waves would go cross the atmosphere to the transmitter on the right, or the receiver, excuse me, on the right, and the whole circuit would be completed by the fact that the receiver and the transmitter, excuse me, were grounded. Okay, so the flow of energy in the upper diagram is clockwise. This bothered Tesla no end. And what really bothered Tesla was the fact that he realized that all of the electromagnetic waves radiating off of an antenna are going in every direction. And only a small percentage of the energy that is radiated from the transmitter ever winds up coming to the receiver. And Tesla thought this was incredibly wasteful. So thinking like a maverick, Tesla did what you see in the bottom diagram. Rather than maximize the electromagnetic radiation that went up the antenna, he maximized the electric oscillating current that traveled through the ground. So his idea was to send energy wirelessly through the Earth's crust. And so his vision in this bottom diagram is counterclockwise. The energy flows from the transmitter through the ground to the receiver, and then the antennas create a return through the atmosphere. Now, to test these ideas out, Tesla couldn't do it in New York City because there were too many distracting currents in the ground. There were, telephone lines and power lines and all sorts of things. He needed to go out to the country, and he chose in 1899 to move temporarily to Colorado Springs so he could test out this big idea. Now, Colorado Springs is on the eastern slope of the Rocky Mountains, which turned out to be just perfect for Tesla, because while he was there, Tesla got to observe lots and lots of big thunderstorms. And he watched how the lightning struck, and he made calculations based on the lightning strikes that he could see. And he realized or decided that he could send electromagnetic energy through the Earth by setting up a stationary wave, and in so doing, he'd have minimal losses. He could propagate energy anywhere, broadcast it anywhere around the world through the Earth's crust, and he thought with minimal losses. He also realized while he was out of Colorado Springs that the minimal losses would come about if he used as his fundamental wave the resonant frequency of the Earth. Okay, so this became his ideal. This became his golden principle that he used to guide everything he did in wireless power. Now, what's interesting in Colorado Springs is, unlike all of the newspaper interviews and all of the publicity that Tesla did in the years before that, he had no public demonstrations in Colorado. He had no witnesses, and he made no attempts to disconfirm his idea about setting up stationary waves through the Earth. He was absolutely confident that this is the way to go. He returns to New York in 1900, and he promptly announces in the newspapers that he will transmit power and messages across the Atlantic in the next 8 months. And to promote his ideas, he writes a long article titled The Problem of Increasing Human Energy, in which he describes all of his inventions, and he declares that he has now addressed every problem that faces humanity. And he published it in a magazine, Century Magazine, which at that time was similar to the New Yorker or the Atlantic magazine today. Confident of his success, Tesla moved into the luxurious Waldorf Astoria Hotel. He ate in the finest restaurants. He rubbed elbows with the rich and famous in New York. And he also announced to the newspapers that while he was in Colorado, he was convinced that he had received messages from Mars, and that there was intelligent life, as far as Tesla was concerned, on Mars. I tend to think that when he gets back to New York at this point, his illusions get ahead of his ideal. That Tesla believed that if you said and you did all the right things and you look like a winner, then the technology and commercial success was sure to follow. Well, success followed him up to a point. In 1901, Tesla secured a loan of $150,000 from JP Morgan. And in return, Tesla wrote into the contract, this was Tesla's decision, to give Morgan 51% of the patent rights that Tesla had for wireless power. With the money, Tesla built a transmitting station on the North Shore of Long Island, near a small village called Wardenclyffe. And the actual building that you can just see in the picture on this slide still exists. And there's a group in Long Island that are restoring the building. The tower was destroyed during World War I. Now, the tower is what everybody gets excited about. It was 187 feet high. It was very impressive. But the real deal for what Tesla wanted to do with wireless power concerned digging the 120-foot deep shaft that went down underneath the water table. And there, Tesla hoped with the series of pipes that projected out from the bottom of the shaft, he could, in his own words, get a grip on the earth and shake it electromagnetically, pump electromagnetic energy into the earth and have it broadcast, propagate everywhere. Now, Tesla, as I mentioned a moment ago, is not the only one who's been inspired by Hertz and working and experimenting with electromagnetic waves. His major rival, Marconi, had been doing the same since 1895, and he focused on a communication system, not a power system, and in particular, a system that was going to be wireless telegraphy. Not wired telegraphy, but wireless telegraphy. And Marconi, in order to attract investors and support, first in Italy and then in the United Kingdom, basically increased the transmission distances that he was using, first across his father's estate, then a few miles, then 20 miles, then the English Channel. But as Tesla made bold claims in New York in 1900, Marconi decided that he needed to be the first to send a message across the Atlantic. And indeed, in December of 1901, while Marconi and his assistant were in St. John, Newfoundland, they detected a Morse code message that had been sent by the Marconi station in Cornwall, England. The newspapers were still waiting for a big demonstration, a big announcement from Tesla. It hadn't come along. And as a result, the newspapers eagerly celebrated Marconi as the inventor of wireless telegraphy. And ultimately, Marconi, not Tesla, got credit for the invention of radio. So if you're Tesla and you've been scooped by Marconi, what do you tell your financier, Morgan? In response to Marconi's transatlantic demonstration, Tesla proposed a new business strategy. He was going to create a world telegraphy system. And as he told Morgan in 1902, what he wanted to do is he wanted to build transmitting stations outside of every major city, New York, Tokyo, Paris. And he wanted to have those stations connected to the cities so that news stories, fax messages, telegrams, even telephone calls could all be transmitted out to the stations. And then the stations would code the information and pump it into the ground. And everybody around the world would have a small receiver, as Tesla liked to say, no bigger than a pocket watch, that they could use. And Tesla wound up this pitch in his letter to Morgan, saying the whole Earth is like a brain, as it were, and the capacity of the system is infinite. You see, Mr. Morgan, the revolutionary character of this idea. Its civilizing potency, its tremendous money-making power. There are three great lines that I tell every engineering student that wants to be an entrepreneur. They have to figure out how to say what their project is going to do. Revolutionary character, civilizing potency, and of course, money-making power. For me, this is the key thing about Tesla. Tesla was the first, as early as 1902, to see that the big story for the second half of the 20th century was going to be the information revolution. And an information revolution that not only reshaped business, but reshaped the lives of ordinary individuals, that individuals would have access to vast amounts of information. How did Tesla, or at least the newspapers, envision this? I love this newspaper story from 1904, and I call your attention to the fact that on the one side of the tower, there's several people. There's a man who's gone camping. There's people in a sailboat. But the one I love best is the oval down on the bottom, which shows a well-dressed lady, perhaps on vacation, and she wants the latest news from her friends back in the big city, back in New York. And to get that information, she has the little receiver, no bigger than a pocket watch, but she just holds up her umbrella, her parasol, and that serves as the antenna to collect all the information. But the vision is information for ordinary people. Morgan and Tesla thought that this was a great idea, and they set up a company that was going to make money by manufacturing and selling the receivers. But before they got very far along, another inventor in the radio space, Lee DeForest, teamed up with a businessman, Abraham White, set up a company and sold lots and lots of stock shares in their company. But White was corrupt, and he ran off with all of the shareholders' money and never built the network that he promised. People on Wall Street, including Morgan, became very nervous that there was a speculative, corrupt bubble around radio stocks, wireless stocks, and they basically said that they wouldn't touch wireless companies, including Tesla's, with a 20-foot pole. In 1903, Morgan basically told Tesla no more money. And over the next 2 years, Tesla fired off a series of angry letters to Morgan, some pleading for money and some attacking Morgan. At the same time, Tesla's personal life fell apart. His closest friend, Richmond P. Hobson, who was a naval officer, had decided he wanted to run for Congress, but to do so, he had to get married, and he married a young woman named Griselda. Tesla had a nervous breakdown, and the way we know it is through a series of letters, many of which were signed Nikola Busted. But you might ask, as engineers, would Wardenclyffe have worked? You know, in other words, and the way to answer this question is the Earth like a water balloon, or is it like the ocean? And the issue here is as electromagnetic energy flows through the Earth's crust, is the crust an inelastic or elastic medium? Tesla thought it was an inelastic medium, much like a water balloon. And the picture here, which you see the little hand on one side, is operating a pump. And the Earth, in his mind, in Tesla's mind, is functioning like a water balloon. And if you had a water balloon filled up with a fluid, and you started pumping on one side, and you reached the resonant frequency of the vessel here, the balloon or the sphere, Each subsequent pump after a certain point, those one-way valves that are sprinkled across the surface of the sphere, with each pump, a little bit of water would squirt out. But that presupposes that the Earth is an inelastic medium as far as from a standpoint of electromagnetic propagation. The reality, of course, is the Earth is much more like an ocean. If you introduce electromagnetic waves at one particular place, like standing on the shore of the ocean and you throw a stone in, the waves go out for a certain time through the ocean, but eventually they peter out, they disappear. The energy is lost. Tesla never understood that. He, to his end, thought that the Earth was like a water balloon and filled with an inelastic medium. In his later years, Tesla worked on a variety of inventions, but after 1905 and that nervous breakdown, he was never the same again. In the 1930s, he had a brief moment of celebrity when he claimed that he had created a particle beam that could shoot down weapons, shoot down airplanes, and Tesla died in 1943. I think Tesla would be thrilled today to be at a conference like the Wireless Power Week, learning about all the different applications, all the different approaches to wireless power. And he would be telling us to dream boldly, but think hard. And I know Chris and JC have come back on. I'll leave you with this final quote, which I think is very important as we think about Tesla's legacy. It comes from a radio engineer, a fellow scientist, in the 1940s. And John Stone said of Tesla, "I think we all misunderstood Tesla. We thought he was a dreamer and a visionary. He did dream, and his dreams came true. He did have visions, but they were of a real future, not an imaginary one. And all of you are fulfilling that Tesla's dream, and you're making his visions happen for a real future." Thank you. I appreciate the extra time to finish up here.
Thank you very much, Dr. Carlson. And in the case of, in the interest of the time, I think we have one question. Okay, I will just read it out. It is interesting to see how Tesla was perhaps the first man to think about the end user in the communications and power transfer industry. Exciting how at the beginning of the 20th century, Tesla was already thinking about the size of the receiver that could have a real visionary, that could have a real visionary man. So it's not so much a question, but a comment. This is the second time I heard your talk. And this time I got some new thoughts. I thought that when you mentioned about Tesla decided not to study Maxwell equation, but build a gizmo, I think many students probably agree with me. They don't want to study Maxwell equation. And maybe we can have a catchy name for our conference in the future, called it Money Making Wireless Power.
Oh, I think you should go with civilizing potency.
And I appreciate that Tesla is a maverick, and he always thinks outside the box, and he wants to accomplish his goal and task as his first priority, and try every way to do it. Of course, we don't recommend everybody have a nervous breakdown, but it takes some time. It takes something to be successful. So we have a second comment, AC electricity enough for us to, so this is more like a comment. So the question is, what was the missing technology that Tesla time that has been missing for realizing his dream? So if something that he could have at that time, maybe the whole world would be different.
So I think that what he was missing, because again, what he wanted to do was transmit the energy through the earth, and I think that he struggled with coming up with a way of efficiently transferring the energy from his transmitter at Wardenclyffe down into the shaft and through the Earth's crust. And that was the missing piece. You can indeed send electrical energy or radio waves through the Earth's crust, because indeed the United States Navy from the through the 1980s and 1990s took advantage of the Schumann cavity and did exactly what Tesla wanted to do, which was transmit very long, extra low frequency waves, what they called ELF, through the Earth's crust, and use that to be able to communicate with nuclear subs that were traveling under the water, and they didn't want the subs to surface. So what he had in mind for the Earth's crust, broadcasting energy or radio waves through the Earth's crust was feasible, but it required, at least in the case of ELF, a very large antenna array that was something like, I used to teach at Michigan Tech, and the antenna array was just over the border from Michigan Tech in Wisconsin, and the array was something like 70 miles wide and 70 miles long. It was huge, and it was figuring out what's that transducer that gets the energy into. Transducer is probably not the right word, but what's the device? What's the technology you need to get the energy into the Earth's crust? That's the missing link for Tesla.
I see. Thank you very much, Dr. Carlson, today for your insight. Our time is up. Our technical section will start very soon. And I'd like to encourage all the researchers. I purchased the book a long time ago, and I read it a few times. It's very fascinating to see how a genius and visionary think and live through history. And that could also teach us lessons. And also, I would like to encourage a researcher here that work harder. There will be somebody like Professor Carlson write about you in the future. Okay. So I will pass my session to Professor Costanzo and Professor Humer, and they will start the technical section 2. And thank you very much, Dr. Carlson.
Now, thank you, JC, for the kind remarks, and thank you to everyone who took time to tune in for this today. And if you have other questions, feel free to reach out to me at the University of Virginia, where I'm part of the engineering school. Thank you again.
Thank you.
Thank you, Bernard, again. Very interesting talk. Thank you. Thank you. Ladies and gentlemen, welcome to the technical session TS2, Rectifiers and Rectennas. I am co-chairing the session together with Professor Remur from the University of Bordeaux. And we will start to show the 2 slides presentation. I hope that all the speakers are present. And then at the end, we will have the question and answer. So I will share my screen. Do you see the screen?
Not yet.
No, not yet.
Now, yes.
No. Oh, yes.
Yeah.
Okay. Okay. Thank you.
So we will ask the speakers to give only a brief introduction of each of their work in no more than 2 minutes, if possible.
Yes.
Thank you very much.
The first paper is, okay. You can start, Simon.
So yeah, the first paper is from Nachiket. Can you introduce your work, please?
Yes, sure. So hello everyone, I am Nachiket Iyer from Tampere University, Finland. I'll present a brief summary of my paper titled Joint Impact of Input Power, PAPR and Load Resistance on the Receiver Efficiency of Multi-Sign Waveforms in RF Energy Harvesting. Yeah, I can begin. Yes. So we know that the receiver efficiency in RF energy harvesting is dependent on numerous parameters such as the peak to average power ratio of the waveform, its shape, the input power to the receiver, and the load resistance. In this work, we have experimentally determined the joint impact of the input power, PAPR, and load resistance on the receiver efficiency of multi-sign waveforms for RF energy harvesting. For this purpose, we have developed a testbed that can determine the receiver efficiency of any digital baseband waveform in RF energy harvesting. It is an SDR-based testbed. Using this testbed, we have evaluated the efficiency of multi-sign waveforms over a wide range of PAPR, load resistance, and input power. We have selected multi-sign waveforms because in literature, they are considered to be ideal for RF energy harvesting. The key results of this work have been tabulated in here. We observe that if the input power is low, then high PAPR multi-signs are indeed optimal, given that the load resistance is large. If the load resistance is low, then high PAPR multi-signs are not optimal, even in the low input power region. On the contrary, in the high input power region, we observe that a simple sinusoid, that is a low PAPR signal, is optimal when the load resistance is low. And when the load resistance is high, even a simple sinusoid is not optimal. So we find that the waveform which is optimal, it depends on the kind of waveform, that is the PAPR, the input power, and the load resistance. We observe that high PAPR multi-signs are suitable for low input power and large load resistance. On the contrary, low PAPR or a simple sinusoid is optimal when the input power is high and the load resistance is small. And in the intermediate region, the optimal receiver efficiency is obtained by lower PAPR waveforms when we increase both the input power and the load resistance to the load resistance of the circuit. Thank you. So this is a brief summary.
Thank you very much, and thank you for being right on time. So we'll come to question a bit in 25 minutes. But now we are going to listen to Lichen Yao. Lichen, can you introduce your work, please?
Yes. So thank you. My name is Lichen Yao from Eindhoven University of Technology. So the paper is about the analytical optimal load resistance calculation of RF energy rectifiers. So can please go to the next slide. Thank you. So this work is motivated by the fact that there exists an optimal load that maximizes the rectifier efficiency. So this is also partially covered by the first presenter. So we try to provide an analytical method to calculate the optimal load so that we don't need to have to do a load of simulation before we can do that. So the key result, first one is that we derive a numerical method that has very low computational complexity based on an analytical rectifier model. And furthermore, we also derive closed form solution to the same problem for a small input signal. And the result is validated for both half-wave and voltage doubler topologies, and with different signals such as continuous wave and multi-sign input signal. So to do this, we firstly model the harvested power using an analytical model based on a low output ripple assumption and Lambert W function with realistic diode equivalent model, which contains all the parasitics. And the closed form method is further derived by making use of the perturbation method as you would use when solving an nonlinear ordinary differential equation. So in conclusion, we propose low complexity methods to calculate the optimal load for analysis without even needing a circuit simulation. So thank you, that's all.
Thank you very much. I have a lot of questions for those two work, but let's wait for the panel. Now we are going to listen to Mahmoud. Can you introduce your paper?
Mahmoud? Is there any authors from the paper entitled Dispenser? Okay.
Okay, great.
Thank you. Please.
Right. So my name is Mahmoud Wagi and I'm from the University of Southampton. And in my paper, I'll be presenting our work on powering Internet of Things devices uses flexible and printed energy harvesting rectennas. Next slide, please.
Yes. Do you see the slide?
Yes. Our devices and those devices need energy.
We can't hear you.
Mahmoud, maybe you could switch off your camera.
Yes.
And try to speak again. Okay, so what we could probably do is wait till Mahmoud is able to has a better connection and to move to the next paper. From Atsuya Hirono. Atsuya, are you here and able to introduce your paper, please?
Yes, hi.
Thank you very much.
I'm Yuki Muramoto from Kanazawa Institute of Technology. I will talk about the 2.4 GHz band SOI CMOS high power bridge rectifier IC with a cross-coupled CMOS pair. Please next page. Thank you. First of all, I will talk about the goal of our study. The RF rectifier is a key component to realize a highly The RF rectifier is a key component to realize a highly efficiency microwave power transmission system. The upper left figure shows configuration of bridge rectifier. RF rectifier is required with high power operation and high rectification efficiency. Next, I talk the methods. The bridge rectifier employs cross-coupled CMOS pair as a diode which has low threshold and high breakdown voltage. The under left graph shows cross-coupled CMOS pair. Next, I present key result of measured rectification efficiency. The upper right graph shows rectification efficiency versus input power. The red solid line shows this work of rectifier IC with CCP. Black dotted line shows past work of rectifier IC with GAD. Measured rectification efficiency of rectifier IC with CCP is higher than that of the rectifier IC with GAD. Finally, I will conclude my presentation. CCP has a low threshold and high breakdown voltage. Measured rectification efficiency of the IC with CCP is 50% at 24 dBm, which is higher than rectifier IC with GAD. The rectification efficiency is the top level performance in 2.4 GHz band 1 watt class SOI CMOS rectenna. Thank you.
Thank you very much. Maybe we could try to hear again from Mahmoud.
Hopefully no connection problem this time. I hope you can hear me well.
Works well.
Okay, so I'll keep it brief this time. Our work is basically about charging energy storage devices for the Internet of Things using flexible and printed rectennas, like what you can see in our photograph in the slide. The idea is we want to intermittently charge the devices, but we want them to stay on after we stop charging them using the RF power. Our method is to have a printed, flexible, and high efficiency antenna on a low-cost substrate, a high efficiency, well-matched rectifier, and our key point is that we eliminate the DC to DC power management stage. And the result has been to achieve the best ever wireless charging efficiency or RF charging efficiency of supercapacitor at 2 frequency bands below 1 gigahertz, being 433 megahertz and 950 megahertz. So as you can see in our key results figure, over the RF input range from 0 dBm to 15 dBm, all above 1 milliwatts of RF power, we have the highest efficiency compared to recent work. And this is because of eliminating the losses in the DC power conversion stage and also enabling these devices to be charged in a much faster and more rapid way. In my full presentation, you can learn more about our proposed optimal design strategy for RF charging, how eliminating the DC to DC conversion can improve the efficiency, how we've achieved cost, size, and also efficiency gains based on our design methodology. And finally, the two applications we have deployed our Rectenna in: far field power transmission, as well as near field ambient energy harvesting. And also in my full video, there are a bit of notes on the ongoing work, the ongoing challenges, and finally the future work to improve this proposal. Thank you.
Great, thank you very much. So we could now move to Huib Visser. Can you introduce your paper, please? So we are now calling from Huib Visser.
And Cord Hammoud, no one of the authors are present.
Actually, Huib is already on the panel, so we should hear him. Okay, so probably we move to the next paper and we'll come back to him later.
Yes. Okay, the next paper is entitled Analysis of Millimeter Wave Rectifiers with Accurate Rectification Model. Please, Siping Gao, can you introduce your paper?
Yes, thank you, Chair. Good morning, good afternoon, and good evening. This is Siping Gao from National University of Singapore. I will be talking about our work on analysis of millimeter wave rectifiers with an accurate rectification model. Could you please turn to the next page? Okay, thanks. Millimeter wave wireless power transfer systems operating at 35 and 94 gigahertz are desired for its small footprint and lightweight, which find application in the mid-range WPT like the UAVs. On the other hand, a rectifier is a building block for WPT system. To facilitate high-efficiency millimeter wave rectifier designs, we employed a lookup table-based automated rectifier synthesis method. The lookup tables are essentially rectifier key performance indicators such as efficiency and the input impedance of the diode over a 2D plane of load resistance in the x-axis and the input power in the y-axis. In this work, a brief survey of commercial Schottky diodes first reveals that the MACOM MA4E1317 is a good candidate to work up to 100 gigahertz. Second, we employ this lookup table-based analysis method on MA4E1317 based rectifiers. It turns out that the theoretical limit on the RF to DC conversion efficiency is 83 at 35 gigahertz and close to 80% at 94 gigahertz, both of which are much higher than the reported efficiencies. Moreover, the input impedance is close to 50 ohm at 95 gigahertz, indicating that the impedance matching is easier at higher frequency. With the powerful lookup table-based method, we can expect more than 70% millimeter wave rectifier to be realized in the future. Thank you.
Thank you very much. Is Huib present, Becker? Otherwise, we can switch to paper number 8. Oh, Huib, are you here? Okay, perfect.
Can you hear me?
Yes, yes, yes. Please.
Okay. Sorry for that. I had a bit of problem with unmuting. But it's solved. This paper is work that's mainly done by my master student or former master student, Coder Hammoud, and it's about going practical Rectenna systems. Okay, can you please move to the next slide? Thanks. We had some experience with Rectennas that were performing very well in terms of efficiency and distance, but they couldn't be used very well in systems because you needed to have a freestanding antenna, and they were quite large, 6 by 10 centimeters. So we set out to make a smaller antenna, a Rectenna on a grounded substrate operate so that you can have some electronics behind it. So it's all about compromises. We make an antenna that's 50 ohm. We have an impedance matching network, and that gives us the possibility to change diodes and matching network components. And on top of that, we have looked at methods to also transfer information. Because of all the compromises, our antenna is extremely small band. So we have used the approach of direct antenna modulation, which is basically switching on and off the antennas to get information over a wider bandwidth than the bandwidth of the antenna. And shown in the paper are the results of replacing the diodes to get the better efficiency, and the first test with direct antenna modulation. And on the picture in the right bottom corner, you see the system being used by my co-author. Small antenna connected to a display displaying the results of a temperature sensor. So that's about it. Thank you.
Thank you. Thank you very much. We discussed it during the panel session. The next presentation is the development of Class R rectifier for microwave wireless power transmission to EV trucks. Please, Koki Miyawatashi and Naoki Shinohara.
Can you hear me?
Yes, please.
Okay, thank you. I'm Koki Miyatashi from Kyoto University. EV trucks are effective means for solving environmental problems. The MPT system for EV trucks has been proposed. The basic frequency is 5.8 gigahertz. The rectangular size is 2.2 meters by 6.5 meters, and the DC power is 50 kilowatts in the system. We design rectifiers in the system. The required conditions of the rectifier are output power of 8.7 watts or more and RF to DC efficiency of 80% or more. We focused on Class R filter in designing the rectifier. The impedance from our diode to Class R filter is pure reactance of JX. So Class R filter processed harmonics or easier than Class F filter. We designed and compared Class R and Class F single shunt rectifiers by ADS simulation. As a result, the RF to DC efficiencies of 87.1% for Class R rectifier and 86.4% for the Class F rectifier were obtained. We confirmed that the design Class R filter meets the requirement. Thank you.
Thank you very much. The next paper is entitled the Nanopower Self-Clock LDO for RF Energy Harvesting. Christos Konstantopoulos. Christos.
Yeah, perfect. And just to introduce myself.
Please.
I'm Christos Konstantopoulos. I come from University of Innsbruck, and I'm going to present my work. Our work is about a nanopower self-clock digital load dropout regulator for RF energy harvesting. Our goal was the integration of the digital load dropout regulator in a system on a chip for IoT. It should be able to interface an energy harvesting unit. It should be able to power the system on a chip system clock, as well as and the other mixed signal loads of the system on a chip, as well as being self-charged up. Of course, it should be able to have an optimum integration of the in-regulator oscillator into the DLDO. The method was an asynchronous fine and synchronous coarse regulation. This actually gave us a robust course regulation, a ripple unbounded from the sampling frequency, and the burst oscillator was based on a multivibrator. The burst response under a transient was unbounded from the sampling frequency. And also an optimized power on reset circuit was designed. The key results was a test bench that actually proved that the DLDO is able to start up from as low as minus 27 dBm rectified power. It was accompanied with the rectifier as seen, and the load test bench. It gave us a maximum power efficiency of 88.5 at the 26 microampere load. And it was able to operate from 500 nanoamperes to 100 microamps. The quiescent current was 375 nanoamps. So just a conclusion, we have shown a high power efficient voltage regulation at 0.5 volt. The DLDO is of nanowatt operation. It is a self-clock design, and it is able to have an optimum integration into the system on a chip dedicated for Internet of Things applications.
Thank you very much.
You're welcome.
The last paper is transparent and flexible self-dual antennas for hybrid inductive, capacitive, and radiative power transfer by Yang Zhu. Please, Yang Zhu.
Hello, hello everyone. My name is Liang Zhu, a student of Dr. Pen Chen from University of Illinois at Chicago. So my topic is about the transparent and the flexible self-dual antennas for hybrid inductive, capacitive, and also radiative power transfer. So our primary goal is right now, nowadays, we have different types of wireless power transfer system, especially from the coupling mechanisms. First one, we will have this capacitive wireless power transfer. Typically, we use the metal pad as a transmitter and another metal pad as a receiver, and use this method to do the near field capacitive coupler. And we can include the matching circuit and also the rectifier to do this capacitive wireless power transfer. And also, we can, instead of this metal pad, coil can be utilized to do this inductive wireless power transfer. And also, most recently, two types of the far field radiative power transfer and also this near field mechanism can be combined together to form the hybrid WPT system. However, to date, most of the system are working on the opaque metals, which means will definitely limit the future applications of this WPT system, especially for the device integration and also multifunction devices. For example, integration with the solar cell as the cold energy harvester. So here we propose to use the optically transparent antennas to make the wireless power transfer system. So in our design, first we use the nanocircuit method and also this impedance locus to boost the optical transparency of our material, and also with the decent electrical conductivity. And then we use this transparent material to make the tri-band inductive wireless power transfer system, and also this tri-band capacitive or hybrid capacitive wireless power transfer system. So our primary method is at first, we instead of using the silver, here we try to dope some copper inside of the silver, and we can minimize the optical loss inside of this material. So we can improve the optical transparency. And then we can sandwich this doped material into two dielectric layers, and then further boost optical transparency of the material. Also, this dielectric can serve as a protection layer for the antenna. And we can also use our nanocircuit model to fast approximate this transmittance. And also, finally, we use this DMD conductor to make different types of the wireless power transfer system. Yeah, that's all. Thank you.
Thank you very much. Okay, so I think we can now start with the questions. Simon, would you like to start with the first? We have many questions, so we can start from the first one to question each paper. Do you agree with this?
Yeah, now, Alessandra, we are seeing your screen. Maybe you could share the slide from TS1 during the question so that the author would use it in background.
Okay. Do you see my screen now?
We see your whole computer screen, not only the document. If not, you can just unshare your screen and the presenter will be able to do it.
You check the question, okay?
Okay, so yeah, that's perfect. Thanks, Alessandra. So maybe we can start with the first presentation. Actually, it was on Papr. And one question that has been raised by the audience on the WUVA website was about matching. So you've been investigating different kind of load, but for different power, you would have a different operation of your nonlinear device. So can you comment on what would you need to do on the matching side to have the best efficiency?
Yes. So I think I guess you already replied yourself there. So yeah, the matching the matching efficiency is actually a function of the input power as well. And any matching network that usually we design is optimal for a single input power. Then ideally, in a practical scenario, whichever sensor that we develop, a receiver sensor, it is usually matched to a single input power that it may receive. But again, that is not fixed in a wireless scenario that it may receive. Yeah. But I would say that yes, matching network that we have used in our circuit is, I guess, a 50 ohm one, because the receiver we have used is an off-the-shelf one from PowerCast, and it is designed to be optimal at 915 megahertz, around 0 dBm power. But yeah, it gives reduced efficiency at other input powers. And in this paper, we are basically trying to determine the performance of the entire receiver, which also includes the matching network.
Thank you.
Okay, thank you very much. So we are going to move now to paper TS2.2. And maybe I would have a question on the relationship between the input power and the efficiency. Can you comment on that?
So if I understand the question correctly, you mean how would the input power influence the overall efficiency of the rectifier? Is that correct?
Yeah. Could you explain why there is a relationship between input power and efficiency based on what you found on your model?
So it's majorly down to the nonlinearity of the diode. Because of the IV characteristic of the diode is an exponential shape. So the amount of voltage that's applied across the diode actually influence the amount of current and ultimately also influence the resistance of the diode that's shown to the circuit. So when the input power is low, meaning that induced the voltage across the diode is very low, because of the exponential curve of the diode characteristic, the resistance of the diode will be very high. So there will be a high loss and dissipation on the diode. And if you increase the input power, then the operational points of the diode moves to a more efficient region where the resistance drops a lot. So that's why in general, the diode would have a better efficiency if the power is higher. but that will stop somewhere because when the power is high enough, then the diode will reach its saturation region. Then the diode will break down, so the harvest power will not be increased anymore with the input, with the increased input power. Yeah.
Okay, thank you very much for your reply. So if we have some time, we will see if we can come back to your paper. And now we would need to move to the paper to TS23. Mahmoud, can you hear? Can you hear us? Okay, great. So there's a question that's been raised, and I'm going to read it. For the measurement, did you measure the performance for different incidence angle and different polarization of the incident wave? And would it be interesting to find the average efficiency over incident angle and polarization?
Yeah, I think that's definitely an interesting use case. We have not experimentally investigated this in this work, but from simulations, the antenna being based on a monopole antenna is going to have an omnidirectional radiation pattern. So over 360 scan around the antenna, you would expect the antenna to have a high average gain. And overall, you would expect a high average radiated power. And similarly, a high average DC power because the gain pattern of the antenna doesn't change significantly due to its omnidirectionality. In terms of polarizations, the antenna is linearly polarized. So the antenna will only be able to realistically harvest polarizations that is aligned with the incident polarization. So for example, if that's aligned vertically, so it will only be able to harvest vertical or circular polarizations with a 50% loss. In some of my previous work, we have actually measured the DC power output of an omnidirectional antenna and related it to the simulated gain from CST simulation. And we found the two curves to fit nicely. So I'll put that link in the chat. But it's something that will come in our future work, mainly as part of improving the energy harvesting antenna in this rectangular design.
Would you have any ideas on how to improve both the gain of the antenna while keeping a high efficiency and covering all of the sphere?
Yeah, we can increase the number of elements. So it can't be done with a single antenna. So it will have to be a design which uses multiple semi-directional antennas. So for example, a design like a bit like a microstrip patch antenna or kind of an antenna array structure where you'll have multiple narrower beams all combining into multiple rectifiers or in a single rectifier. For the polarization, it will simply be having a dual polarization antenna, a vertical polarization port connected to a rectifier, a horizontal polarization port connected to a separate rectifier, and then some form of a power combining circuit, which eliminates the losses when one of them is significantly higher than the other to prevent leakage into the other rectifier circuit, basically.
Okay, thank you for your suggestion. Thank you very much. We are going to move to the next paper. A question would be, how do you compare your work to other circuits that are using gas diodes or even GaN transistors?
Sorry, I don't understand. So could you speak in simple and slowly?
So you have been developing a circuit using CMOS technology?
Yes.
The question is it better or worse than gas diodes? Is it better or worse than GaN, gallium nitride transistors?
Okay.
How do you compare your work with the previous ones? This question is also posted on the site, so you can try to answer directly to this question on the site.
Yeah, I also think that's the best way. So please just go onto the Wova platform and answer to the questions that have been posted related to your paper. Thank you very much. So maybe we move to the paper TS25. And the question that I would have is about the diodes package and the diodes that have been used for fabricating the circuit. So would you be able to comment on this?
Yes. Does my unmute work this time? Can you hear me?
Yeah,
Yes.
We hear you perfectly.
Okay, great.
Well. So the question is similar to the one that has been posted on the website.
Yeah.
But it's for everyone to benefit from your answer.
Okay. Yeah, then your question is about the used diodes and the packaging. In my system, I used the SOT23 package. And the question is, can you improve on the efficiency if you use smaller packaging due to the parasitics? And the answer is, I think you're right. I think that that improvement is possible, but at the same time, although I haven't investigated it, I'm wondering how much improvements you can get, because in the optimization, we already took the parasitics into account. So it's part of the optimization, and going to a smaller package and maybe smaller parasitics, you have to redo the design, and that can give you a bit of increase in efficiency, but efficiency is already quite high. It's about 40-45% at -10 dBm RF input power. And I'm wondering if that's the way forward to really improve the system. I think the improvement will be quite marginal. And I think it's better to look at different types of diodes. What we have done is we used the Avago diodes, because that's what we did in the past. And then we changed to Skyworks diodes with another saturation current. And that gave us about 10% increase in efficiency. So I think the way forward is the type of diodes. And I believe that will do more than the packaging, although the packaging in itself will have an influence. So I hope that answers your question.
Yeah, perfectly. Thank you very much.
You're welcome.
And I agree with you. So we can move now to the next question. Alessandra, do you want me to share my screen so that you could?
Okay, thank you. Okay, for this paper, there is the question about the choice of the topology. If you have also used a voltage doubler using the MACOM diodes, and the justification of why this diodes is the best choice for millimeter waves.
Okay, so to answer your last question, actually, the reason that we choose to analyze this MACOM diode is because it can work up to 100 gigahertz. Yeah, that's the reason, because the junction is relatively small, and the junction capacitance is small, which enable the operation toward the millimeter wave, right? And the topology comparison between voltage doubler and shunt topology in terms of efficiency and impedance in my opinion, voltage doubler can also achieve the same efficiency as those single diode topologies theoretically, without considering the losses introduced by the real implementation. Just that the input power should be doubled and the output voltage is also doubled. That is the feature of the voltage doubler. Yeah, but in reality, of course, using two diodes will inevitably introduce more loss, and the efficiency will be slightly smaller than the single shunt or single series topologies. Yeah, I hope I answer your question.
Yes, thank you very much.
Sure.
Any other question? I don't see more questions on this paper. So the next one.
Okay.
Koki Miyawashi. Miwata. Thank you. Okay. In this case, the question concerns the use of single antenna and single rectifier. Have you checked the coupling between each antenna elements, and why don't you think of a beamforming network to combine each antenna element?
Oh, thanks for the question. We are still considering the structure of the antenna part, but we are planning to use an array antenna for beamforming. The received power by each antenna element can be very small or large. We are still considering using RF combiner or RF dividers, but we have not studied this yet.
And have you think of combining the results in DC instead of at RF?
One more time, please.
Excuse me?
Sorry. Oh, sorry. Can you repeat
I was asking if you have combined the results in DC, and how did you do it?
Oh.
What was the strategy to combine the DC power?
I don't consider in DC power. So
Okay, we can discuss perhaps later.
Thank you.
Thank you. Next one is a nano power self-clock DLDO for RF energy harvesting.
Hello, I'm here. Can you hear me?
Yes.
Yeah. Well, for I see that there is one question, basically two questions.
Yes,
regarding...
I repeat the question. What input power range would you expect in the application that your circuit is intended for? And what resistance range do you expect that the rectifier would like to see at DC? Okay.
Yeah, regarding the first question, it has to do with it has a test bench. The work is focused on the regulator. If we are talking about the input power range that it's before the rectifier, then we could say that it's about minus 20. The lowest power supported for this test bench is about minus 20 dBm. However, it depends on the efficiency of the rectifier. On the other hand, if you are talking about the lowest supported input power, rectified power that comes into the regulator, then we can say that the regulator has a 83.6% power efficiency with minus 27 dBm input rectified power. So yeah, that's the highest power. That's the power that actually works with 3.65 microamps load current. Then for the second question, we can say that the resistance can be for given output load, the input resistance, excuse me, yeah, the output resistance of the rectifier could be as low as that it has 50 millivolts of dropout voltage between the output and the input of the regulator, such that the regulator can work. There is no calculated actually resistance range that I can mention, but that's the point. You have to reassure that there is at least 50 millivolts dropout voltage for given load range. Yeah, that's the answer. Yeah.
Okay, thank you.
You're welcome.
We have the last paper. The first question is related to more comment about the efficiency as a function of incident polarization for the far field case, and also what are the performance variation when in the near field case misalignment and distance variation are experienced.
Thank you so much for this question. So at first, I should say for the polarization, because in our case, all of the antennas we utilized are linear polarization. So in such a case, if we tune the polarization of the incident wave, in that case, especially for the 90-degree, we will have the strong polarization mismatch, which means the efficiency will be very low. And for another case, when it comes to the incident angle, it's directly be related to our radiation pattern. I should say, even though our radiation pattern is not like the omnidirectional radiation pattern for the two inverted F antenna, however, at the higher gain part or higher gain position or higher gain angle, we do have very high overall efficiency of the system. However, if the gain of the antenna is very, very low, for example, even just 5% of the radiation efficiency of the antenna, then the overall system will not work, I should say. And at last, I should say for the misalignment, for the inductive wireless power transfer system with the coil, this system can work in the Z direction or the vertical direction. The distance can even up to like 5 centimeters. However, when it comes to the capacitive wireless power transfer, is very, very short in interrogating distance, just limited to around 2 to 3 millimeters. Because I think we can further improve the misalignment stuff or in the Z direction of the capacitive pack by increasing the overall dimension of the two antennas in the capacitive case. And also for the XY direction, we do have some also misalignment, but the issue is not comparable to the Z direction. Thank you.
Thank you. I also have another question concerning the nano, the model of your nano circuit.
Okay.
How do you use it in the design you have presented in your work?
Okay, so at first, after we dope our material with the copper doped silver, so right now we can decide the two types of the dielectric material in our case. So the primary goal is to tune the capacitance of these two material and to cancel out the reactance of the imaginary part of the copper doped silver. And also another case is not only we directly calculate the open circuit condition, we also check the impedance locus with the nano circuit. Because when we try to tune the thickness of the top layer and also the bottom dielectric layer, we can see the change of our impedance locus. So then we can tune the refraction index of the material and also the thickness of two dielectric coating until we can have this good impedance matching, which means the impedance will reinsect with the real axis of our impedance. Yeah, did I answer your question?
Yes.
Thank you.
Thank you. I don't see new questions in the question and answer.
Yeah, I think that's actually already time to end the session. There's quite a lot of questions already on all of those topics, and we are inviting all of you to go to the WUVA platform and to take part into the question and answers for all of those papers.
Yeah,
so
a very live discussion already.
Yeah, great discussion.
Yes. So we like to thank you, the authors, and also the audience, the panelists, to participate to this session. And we can close it. Thank you. Then enjoy the conference, the next sessions. Thank you.
And everybody, don't forget to come back for the keynote session 3 and technical section 3 in 1 hour.
Yes. Thank you.
Thank you very much, Alexandra and Simon. This is very successful. Thank you very much.
Thank you.
Yeah, thank you. Thank you all.
Bye. Thank you all. Bye-bye.
Bye.
Bye.
Bye-bye.